Hi, I'm a tutor in Uplatz. Today we are going to discuss about Introduction to Assembly Language of ATMEL AVR Microcontrollers, Part 1. While learning assembler, the reason is namely in the following cases. If bugs have to be analyzed, if the program executes different than designed and expected, if the higher level language does not support the use of certain hardware features, if time critical inline routines require assembly language portions, it is necessary to understand assembly language. Example, to understand what the higher level language compiler proves. Without understanding assembly language, you do not have a chance to proceed further in these cases. Wait learning assembler, short and easy. Assembler's instructions translate one by one to executed machine instructions. The processor needs only to execute what you want it to do and what is necessary to perform the task. No extra loops and unnecessary features blow the generated code. If your program storage is short and limited, and you have to optimize your program to fit into memory, assembler is choice one. Shorter programs are easier to debug. Every step makes sense, fast and quick. Because only necessary code steps are executed, assembly programs are as fast as possible. The duration of every step is known. Time critical applications like time measurements without a hardware timer that should perform excellent must be written in assembler. If you have more time and don't mind if your chip remains 99% in a wait state type of operation, you can choose any language you want. Assembler is easy to learn. It is not true that assembly language is more complicated or not as easy to understand than other languages. Learning assembly language for whatever hardware type brings you to understand the basic concepts of any other assembly language dialects. Adding other dialects later is easy, as some features are order dependent. Optimal code requires some familiarity with the hardware concept and the dialect. What makes the assembler sometimes look complicated is that it requires an understanding of the controller's hardware functions. Consider this is an advantage. By learning assembly language, you simultaneously learn more about the hardware. Higher level languages often do not allow you to use special hardware features and so hide these functions. The first assembly code does not look very attractive. With every additional lines program, it looks better. Perfect programs require some thousand lines of code of exercise, and optimization requires lots of work. The first steps are all in any language. After some weeks of programming, you will laugh if you go through your first code. Some assemblers instructions need some months of experience. AVRs are ideal for learning assembler. Assembler programs are a little bit silly. The chip executes anything you tell it to do and does not ask you if you are sure overriding this and that. All protection features must be programmed by you. The chip does exactly anything like it is told, even if does not make any sense. No window warns you unless you programmed it before. To correct typing errors is as easy or complicated as in any other language. Basic design errors, the more tricky types of errors, are also as complicated to debug like in any other computer language. But testing programs on ATMEL chips is very easy. If it does not do what you expect it to do, you can easily add some diagnostic lines to the code. Reprogram the chip and test it. Bye-bye to you EEPROM programmers, to the UV lamps used to erase your test programs, to you pins that don't fit into socket after having them removed some dozen times. Changes are now programmed fast, compiled in no time, and either simulated in the studio or checked in circuit. No pin is removed or no UV lamp gives up just in the moment when you add your excellent idea about that bug. Test it. Be patient doing your first steps. If you are familiar with another higher level language, forget it for this first time. Behind every assembler language, there is a certain hardware concept. Most of the special features of other computer languages don't make any sense in assembler. The first 5 instructions are not easy to learn. After that, your learning speed rises fast. After you add your first lines, grab the instruction set list and lay back in the bathtub and wondering what all, all the other instructions are like. Serious warning, don't try to program a mega machine to start with. This does not make sense in any computer language and just produces frustration. Start with the small hello world like examples. Example, turning some LEDs on and off for a certain time. Then explore the hardware features a bit deeper. Recommendation, comment your subroutines and store them in a special directory. If debugged, you will need them again in a short time. Have success. The concept became the language assembler in microcontrollers, the hardware of microcontrollers. What has the hardware to do with assembler? Much as can be seen from the following. The concept behind the assembler is to make the hardware resources of the processor accessible. The resources means all hardware components like the central processing unit CPU and its max servant, the arithmetic and logic unit ALU. The diverse storage units, internal and external RAM, EEPROM storage. The ports that can control characteristics of port bits, timers, A to D converters, and other devices. Accessible means directly accessible and not via drivers or other interfaces that an operating system provides. That means you control the serial interface or the A to D converter, not some other layer between you and the hardware. As award for your efforts, the complete hardware is at your command, not only the part of that the compiler designer and the operating system programmer provides for you. How the CPU works. And the most important for understanding assembly is to understand how the CPU works. The CPU reads instructions, instruction fetch from the program storage, the flash and translates those into executable steps and executes those. In the AVRs, those instructions are written as 16-bit numbers to the flash storage and are read from their first step. The number read then translates the second step, example, to transporting the content of the two registers R0 and R1 to the ALU, third step, and to add those fourth step, and to write the result into the register R0, fifth step. Registers are simple 8-bit byte storages that can be directly tied to the ALU to be read from and to be written to. How CPU works. The coding instruction is demonstrated by some example. CPU operation, send CPU to sleep, 1001, 0101, 1000, 1000, 9588 is the hexadecimal code. Add register R1 to register R0, 0000, 1100, 000, 0001, 0C01 is the hexadecimal code. Subtract register R1 from register R0. The binary code is 0001, 1000, 0000, 1801 is the hexadecimal code. Write constant 170 to register R16, 1110, 1010, 0000, 1010. EA0A is the hexadecimal code. Multiply register R3 with register R2 and write the result to the register R1 MSB and R0 LSB is 1000, 1100, 0011, 0010. Hexadecimal code is 9532. So if the CPU reads HEX 9588 from the flash storage, it stops its operation and does not fetch instructions anymore. Don't be afraid. There is another mechanism necessary before the CPU executes this, and you can wake up the CPU from that. Executing instructions. If the CPU reads hexadecimal 0C01, R0 and R1 is added to the result, is returned to the register R0. This is executed like demonstrated in the picture. From the flash, 0C01 is taken into the ALU, and ALU, based on that, ALU adds the register R0 and R1, and the result is written into the register R0. The instruction word 16 bit is read from the flash and translated into executable steps 1. The next step connects the registers to the ALU inputs and adds their content 2. Next, the result is written to the register 3. Executing instructions. If the CPU reads hexadecimal 9C to 3 from the flash, the registers R3 and R2 are multiplied and the result is written into the R1 upper bit and R0 lower bit. If the ALU is not equipped with hardware for multiplication, example in any and at tiny 30, the 9C to 3 does nothing at all. It does not even open an error window. The tiny 13 does not have that hardware. In principle, the CPU can execute 65, 16-bit different instructions, but because not only 170 should be written to the specific register, but the value between 0 to 255 to any register between R16 and R31. This load instruction requires 256 to 16 is equal to 4096 of the 68536 theoretically possible instructions. The direct load instruction for the contact C7 to C0 and register R0, R3 to R0, R4 is always 1 and not encoded. Is coded like this. Load R to C is bits 15 to W0 are 111, 0, C7, C6, C5, C4, R3, R2, R1, R0, C3, C2, C1, C0. Why those bits are placed like this in the instruction word remains ATMEL secret. Executing instructions, addition and subtraction request 32 start 32 is 1024 combination, and the target registers are not R31, T4 to T0, and source registers are not to R31, S4 to S0 are coded like this, where T4 to T0 is the code for the registers R0 to R31, S4 to S0 you see code for source registers R0 to R31. Now consider adding RT to RS. The instruction is 0000 11 S4 T4 T3 T2 T1 T0 S3 S2 S1 S0. Subtract RT to RS 0001 10 S4 T4 T3 T2 T1 T0 S3 S2 S1 S0. Please do not learn this bit placement. You will not need them later. Just understand how an instruction word is coded and executed. The instructions in assembler. There is no need to learn 16-bit numbers and the crazy placement of bits within those, because in assemblers you will use human-readable abbreviations for that, so-called mnemonics, and aid to memory. The assembler representation for hexadecimal 9588 is simply the abbreviation SLEEP. In contrast to 9588, SLEEP is an easy to remember. Even for someone like me that has difficulties in remembering its own phone number, adding simply is add. For naming two registers that are to be added, they are written as parameters. No, not in brackets. C programmers forget those brackets. You don't need those in assembler. Simply add R, R1. The line translate a single 16-bit word 0C. 01, the translation is done by the assembler. The CPU only understands 0C01. The assembler translates the line to this 16-bit word, which is written to the flash storage. Read from the CPU from there and executed. Each instruction that the CPU understands as such a mnemonic and vice versa, each mnemonic has exactly one corresponding CPU instruction with a certain course of actions. The ability of the CPU determines the extent of instructions that are available in assembler. The language of the CPU is the base. The mnemonics only represent the abilities of the CPU itself. Difference to the higher level languages. Here are some means for higher level programmers. In high level languages, the constructions are not depending on the hardware or the CPU or the abilities of the CPU. Those constructions work on very different processes if there is a compiler for the language and for the process family available. A compiler translates those language constructions to the process binary language. A go-to in BASIC looks like a jump in assembler, but there is a difference in the whole concept between those two. A transfer of program code to another processor hardware does only work. The hardware is able to do the same. If a processor CPU does not have the access of a 16-bit timer, the compiler for a higher level language has to simulate one, use an 8-bit timer, and sometimes consuming code. If 3 timers are available and the compiler is written only for 2 or a single timer, the available order remains unused. So you totally depend on compiler's abilities, not on the CPU's abilities. Another example, the above shown instruction, MUL, in assembler, the target processor designates if you can use the instruction or if you have to write a multiplication routine. If in a higher level language, you use multiplication, the compiler instruction math library that multiplies every kind of numbers, even if you have only 8 by 8 numbers, and multiply MUL alone won't do it. The lib offers an integer, a long word, and some other routines for multiplication that you don't need. A whole package of things you don't really need. So you run out of flash in a small tiny AVR and you change to a mega with 35 unused port pins or an X mega just to get your elephant lib with superfluous routines into the flash. That is what you get from a simple star without even being asked. Assembly is not a machine language because the assembly is closer to the hardware than any other language. It is often called machine language. This is not exact because the CPU only understands 16-bit instruction words in binary form. The string add or not, comma, R1 cannot be executed, and assembly is much simpler than machine language. Similarities between machine language and assemblers are features, not a bug. Interpreting an assembler. With an interpreter, the CPU must translate the human-readable code into binary words that can be executed. Then the interpreter would first read the text stream A is equal to A plus B, 9 characters of one type, 1 byte each, strip the 4 blanks from the text, locate the variables A and B, location in register or in SRAM, precision, length, etc. Identify the plus sign as operator, prepare a machine executable sequence that is equivalent to the formulation in the text. In the sequence properly, a simple machine code like add R0, R1 in assembler would result, but most probably the resulting machine code would be multiple words long, read and write variables from to SRAM, 16-bit integer, adding, saving, storing, restoring on the stack, etc., etc. The difference between the interpreter and the assembling is that after assembling, the CPU gets its flavored meal executable words directly. When interpreting, the CPU during the most of the time performing the translation task. Translation probably requires 20 or 200 CPU steps before the 3 or 4 words can be executed. Execution speed is not, so is more than lame. While this is no problem if one uses a fast clock speed, it is inappropriate in time-critical situations where fast response to an event is required. No one knows what the CPU is just doing and how long this requires. Not having to think about timing issues leads to the inability of human programmers to resolve timing issues. And missing information on timing keeps him unable to do those things if required. High-level languages and assembler. Higher-level languages insert additional non-transparent separation levels between CPU and source code. An example for such a non-transparent concept of variable. These variables are storage that can store a number, a text string, or a single Boolean value. In the source code, a variable name represents a place where the variable is located, and by declaring the variable, the type, numbers, and their format, strings, and their lengths, etc. For learning assembler, just forget the high-level language concept of variables. Assembler only knows the bits, bytes, registers, and SRAM types. The term variable has no meaning in assembler. Also, related terms like type are useless and do not make any sense here. Higher level languages require you to declare variables prior to their first use in the source code. Example as byte, 8-bit, double word, 16-bit integers, 15-bit plus 1 sign bit. Compilers for that language place such declared variables somewhere in the available storage space, including 32-bit registers. If this placement is selected rather blind by the compiler, or if there is some priority rule used, like an assembler programmer calculates it, is depending more from the price of the compiler. The programmer can only try to understand what compiler thought when he placed the variable. The power to decide has been given to the compiler. That relieves the programmer from the trouble of that decision but makes him a slave of the compiler. The instruction A is equal to A plus B is now type proofed. If A is defined as a character and B is a number, example is equal to 2, the formulation is not accepted because character code cannot be added with numbers. Programmers in high-level languages believe that this type check prevents them from programming nonsense. The protection that the compiler provides in this case, prohibiting your type error, is rather useless. Adding 2 to the character F, of course, should yield H as a result. What else? Assembler allows you to do that, but not compiler. Assembler allows you to add numbers like 7 or 48 to add and subtract to every byte storage, no matter what type of thing in the byte storage. What is that storage is a matter of decision by the programmer and not by a compiler. If an operation with that content makes sense, it is a matter of decision by the programmer, not by the compiler. If your registers represent the 32-bit value or 4 ASCII characters, those 4 types bytes are placed low to high or high to low or completely mixed, just up to the programmer. He is the master of placement, no one else. The types are unknown. All consists of bits and bytes somewhere in the available storage place. The programmer has the task of organizing, but also the chance of optimizing. Of a similar effect or all the other rules that the high-level programmer is limited to. It is always claimed that it is a saver of the and of a better overview to the program. Anything in subroutines to not jump around in the code, to hand over variables as parameters and to give back results from the functions. Forget most of those rules in assembler. They don't make much sense. Good assembler programming requires some rules too, but very different ones. And what is the best? Most of them have to be created by yourself to help yourself. So welcome in the world of freedom to do what you want, not what the compiler decides for you or what theoretical professors think would be good programming rules. Higher level programmers are addicted to a number of concepts that stand in the way of learning assembly. Separation in different access levels in hardware, drivers, and other interfaces in assembly. This separation is complete nonsense. Separation would urge you to humorous workaround if you want to solve your problem in an optimal way, because most of the high-level programming rules don't make sense, and because as even puristic high-level programmers break their own rules whenever appropriate, see those rules as a nice cage preventing you from being creative. Those questions don't play a role here. Everything is direct access. Every storage is available at any time. Nothing prevents you access to the hardware. Anything can be changed and even can be corrupted. Responsibility remains by the programmer only that has to use his brain to avoid conflict when accessing hardware. The other side of missing protection mechanism is the freedom to do everything at any time. So smash your ties away to start learning assembler. You will develop your own ties later and want to prevent yourself from running into errors. What is really easier in assembler? All words and concepts that the assembler programmer needs is the data sheet of the processor, the instruction, and the port table. Done with the words. On that, anything can be constructed. No other document necessary. How the timer is started is writing timer.start within bracket 8, somehow easier to understand than LDA R16 0x02, how the TCC R0 R16, how the timer is restarted at 0 CLR R16, and how TCC R0 R16. It is all in the data sheet. No need to consult a more or less good documentation on how a compiler defines this or that. No special compiler design words and concept to be learned here. All is in the data sheet. If you want to use a certain timer in the processor for a certain purpose in a certain mode of the 15 different possible modes, nothing is in the way to access the timer, to stop and start it, etc. What is in the high-level language easier to write A is equal to A plus B instead of null R16 or something? Not much. If A and B are not defined as bytes, or if the processor type is tiny and does not understand MUL, the simple MUL has to be exchanged with some other source code as designed by the assembler programmer or copy pasted and adapted to the needs. No reason to import and non-transparent library instead just because you are too lazy to start your brain and learn. Assembler teaches you directly how the processor works. Because you know compiler takes you over your task, you are completely the master of the process. The reward for doing this work, you are granted full access to everything. If you want, you can program a baud rate of 45.45 bps and the UART a speed setting that no Windows PC allows because the operating system allows only multiples of 75. Why? Because some historic mechanical typewriters and those special mechanical gearboxes are fixed selection of the either 75 or 300 bps. If in addition you want one and a half stop bytes instead of either one or two, why not programming your own serial device with assembler software? No reason to give things up. Who is able to program in assembler as a feeling for what the processor allows? Who changes from the assembler to ILM later on? Example, in case of very complex tasks, has made the decision to select that on a rational basis. If someone skips learning assembly, he has to do what he can, stick to the available libraries and program creative workarounds for things that the compiler does not allow, and in a way that assembler programmers would laugh at loud. The whole world of the processor is at the assembler programmer's command. So why do complicated and highly sensitive workarounds on something you can formulate in a nice, learn, aesthetic way? Hardware for assembler, AVR assembler programming. Learning assembler requires some simple hardware equipment to test your programs and see if it works in practice. This section shows two easy schematics that enable you to improve the required hardware and give you the necessary hints of the required background. This hardware really is easy to build. I know nothing easier than that to test your first software steps. If you like to make more experiments, leave some more space for future extensions on your experimental board. If you don't like the smell of soldering, you can buy a ready-to-use board too. The available boards are characters in this section below. The ISP interface of the AVR family. Before we go into practice, we have to learn a few essentials on serial programming mode of the AVR family. No, you don't need 3 different voltages to program and read an AVR flash memory. No, you don't need another pre-programmed microprocessor to program the AVR. No, you don't need 10 I/O lines to tell the chip what you like it to do. And you don't even have to remove the AVR from the socket on your experimental board before programming it. It is even easier than that. All this is done by a built-in interface in the AVR chips that enable you to write and read the content of the program flash and the built-in EEPROM. This interface works serially and needs only 3 signal lines. A CK, a clock signal that ships the bits to the return to the memory into an internal storage shift register, and that ships out the bits to the read from the another internal shift register. MOSI, the data signal that sends the bits to the return to the AVR. MISO, the data signal that receives the bits read from the AVR. The ISP interface of the AVR family, these 3 signal pins are internally connected to the programming machine only if you change the reset, sometimes also called RST or restart, pin to 0. Otherwise, during normal operation of AVR, these pins are programmable I/O lines like all others. If you like to use these pins for other purposes during normal operation and for in system programming, you will have to take care of that these 2 purposes do not conflict. Usually, you learn them decouple these by registers or by use of a multiplexer. What is necessary in your case depends on your use of pins in the normal operation mode. You are lucky if you can use them for in-system programming exclusively. The ISP6 pin are shown in figure. Not necessary, but recommendable for in-system programming is that you supply the programming hardware out of the supply voltage of your system. That makes it easy and requires 2 additional lines between the programmer and the AVR board. Ground is the common ground or negative pole of the supply voltage. VTG is the target voltage, the supply voltage usually plus 5 volts. This adds up to 6 lines between the programmer and hardware, the AVR board. The resulting ISP6 connection as defined by ATMEL is shown on the left. In the previous slide, standards always have alternative standards that were used earlier. This is the technical basis that constitutes the adapter industry. In our case, the alternative standard was designed as ISP10 and was used on the SDK500 board, sometimes also called CAN-DA interface. It is still a very widespread standard, and even the more recent SDK500 board is equipped with the ISP10 as an additional signal to drive in a LED. This LED signals that a programmer is doing his job a good idea. Just connect the LED to a resistor and clamp it to the positive supply voltage. Here is the ISP6 pin and ISP10 pin are shown in this figure. Now moving forward, programmer for the PC parallel port. Now heat up your soldering iron and build up your programmer. It is a quite easy schematic and works with standard parts from your well-sorted experiments box. Yes, that's all you need to program an AVR. The 25-pin plug goes into the parallel port of your PC. The 10-pin ISP goes to the AVR experimental board. If your box does not have 74LS245, you can also use a 74HC245 with no hardware changes, or a 74LS244 or bar 74HC244 by changing some pins and signal. If you use SC, don't forget to tie unused inputs either to ground or to the supply voltage, otherwise the buffers might produce extra noise by capacitive switching. The necessary program algorithm is done by the ISP software. Be aware that this parallel port interface is not supported by ATMEL Studio software anymore. So if you want to program your AVR directly from within the studio, use different programmers. The internet provides several solutions. The programmer for the PC parallel port, if you have already a programming board, you will not need to build this programmer because you will find the ISP interface on samples. Consult your handbook to locate this. Experimental boards, you probably want to do first programming steps with a self-made AVR board. Here are two versions offered, a very small one with an AT13 or a more complicated one with AT90S2313 or ATMEGA2313, including a serial RS232 interface. Experimental board with an AT9013. This is a very small board that allows experiment with the AT9013 internal hardware. The pictures shows the ISP10 programming interface on the left, the LED attached via a resistor of 390 ohms. The AT9013 will pull up 10K on its reset pin 1. The supply port with the bridge rectifier to be supplied with 9 to 15 volt from AC or DC source and a small 5 volt regulator. Here is the diagram shown here. The AT9013 requires no external crystal or clock generator because it works with its internal 9.6 megahertz RC generator and by default with a clock driver of 8 clock and 1.2 megahertz. The hardware can be built on a small board like the one shown in the picture in the next slide. All the pins of the AT9013 are accessible and the external hardware components like LED shown can be easily plugged in. Here is the board. This board allows the use of AT9013's hardware like IO ports, timers, A to D converters, etc. The XML board with an AT90S2313 ATMEGA2313 is shown in figure. For the test purposes, where more IO pins or a serial communication interface is necessary, we can use AT90S2313 or ATMEGA2313 on an XML board. The schematic shows a small voltage supply for connection to an AC transformer and a voltage regulator 5 volt bar 1 ampere. A crystal clock generator here with a 10 megahertz crystal. All other frequencies below the maximum for 2313 will also work. The necessary ports for a safe reset during supply voltage switching. The ISP programming interface here with the ISP10 pin connector. So that's what you need to start with. Connect other peripheral add-ons to the numerous free I/O pins of the 2313. External board with the easiest output device can be a LED connected to a resistor to the positive supply voltage. With that, you can start writing your first assembler program switching the LED on and off. If you do not need the serial communication interface, just skip the hardware connected to the pin 2/3 and 14/16. Do not need hardware handshake signal. Skip the hardware on the pins 14/16 and connect RTS on the 9-pin connector over a 2.2K resistor to 9 volts. If you use an ATMEL AVR 2313 instead of an AT90S 2313, the following changes are resulting. The external crystal is not necessary as that has an internal RC clock generator, so just keep all connection to the pin 4 and 5. If you want to use the external crystal instead of the RC built-in RC as a clock source, you will have to program the fuses of that accordingly. Ready to use commercial programming boards for the AVR family. If you do not like improved hardware and if you have some extra money left that you don't know what to do with, you can buy a commercial programming board. Depending on the amount of extra money you did like to spend, you can select between more or less costly versions for them. So the following selection criteria should be looked at. Price, PC interface, preferably USB, less convenient or durable 9-pin RS-232 requires additional software interfaces for the parallel port of the PC. Support reliability for newer devices. Updates are required from time to time. Otherwise, use it on a nearly dead horse. Hardware features depending on your foreseeable requirements in the next 5 years. The following section describes 3 standard boards of ATMEL SDK500, SDK500 and the Dragon. The selection is based on my own experience and is not a recommendation. SDK200, the SDK200 from ATMEL is a historic board. If we grab a used one, you will get a board with some sockets for 8, 20, 28, and 40 pin devices, 8 keys and LEDs, hot connected to the port D and B, and LCD standard 14-pin interface, and option for attaching a 28-pin SRAM, a RS-232 for communication cable interface for a PC parallel port on one side, and a 10-pin ISP on the other side. High voltage programming is not supported. The board cannot be programmed from within the studio. The programming software is no longer mated, and you must choose external program capable of playing PC parallel port. If someone offers you such a board, take it only for free, and if you are used to operate some software of the necessary kind. SDK500, easy to get is the SDK500 example from ATMEL. It has a column hardware socket for programming most of the AVR types, example 14-pin devices, or TQP package requires additional hardware. A serial and parallel programming in normal mode or with high voltage programming brings devices back to life even if the reset pin has been fused programmed to the normal port input. ISP 6-pin and ISP 10-pin connection for external in system programming. Programmable oscillator, frequency and supply voltage, plug-in switches and LEDs, a plugged RS-232C connected UART, a serial flash EE program from the older boards have this. Access to all ports pins where 10-pin connectors. SDK500, a major disadvantage of the board is that before programming areas, several connections have to be made manually with the delivery cables. The board is connected to the PC using a serial port COMX. If your laptop does not have a serial interface, you can use one of the common USB to serial interface cables with the software driver. In that case, the driver must be adjusted to use between COM1 and COM8 and a baud rate of 115K to be automatically detected by the studio software. Programming is performed and controlled by the recent version of AVR Studio, which is available for free from ATMEL's webpage. After registration, updates of the device list and programming algorithms are provided with the studio versions with support for newer devices is more likely than with other boards and programming software. Experiments can start with they also supply the AVR older version at 90S 8515. Newer board versions include different types. This covers all hardware requirements that a beginner might have. AVR Dragon. The AVR Dragon is a very small board. It has an USB interface, which also supplies the board and the 6-pin ISP interface. The 6-pin ISP interface is accompanied by a 20-pin HP programming interface, high voltage programming interface. The board is prepared for adding some sockets on board, but does not have sockets or target devices and other hardware on board. The Dragon is supported by Studio software and is updated automatically. Its price and design makes it a nice gift for an AVR amateur. The box fits nicely in a row with other precious and carefully designed boxes. Tools for AVR assembly programming. For basic program are necessary for assembly program. These tools are the editor, the assembler program, the chip programming interface, and the simulator. The two different basic routes are possible. Anything necessary in one package. Each task is performed in specific program. The result are stored as specific files. Usually the route one is chosen. To understand the underlying mechanism first, we start with the description of route 2 first. This shows the way from a text file to the instruction word in the flash memory. The editor has a simple typewriter. Assembler programs are written with an editor. The editor just has to be able to create and edit ASCII text files. So basically, any simple editor does it. Some features of the editor can have positive effects, errors that assemblers later detects are reported along the line number in the text file. Line numbers are also a powerful invention of the computer age when it comes to the discussion of your code with someone else. Typing errors are largely reduced if those errors are marked with colors. It is a nice feature of an editor to highlight components of a line in a different color. The more or less intelligent recognition of errors is typing, but this is a feature that I don't really miss. If your editor allows the selection of font, choose a font with set spacing like Courier. Headers look nicer with that. Your editor should be capable of recognizing line ends with any combination of character carried written line by both without producing unacceptable screens. Another item on the wish list for Windows 2013. The editor, if you prefer, as a simple typewriter, if you prefer shooting with cannons to kill sparrows, you can use a mighty word processing software to write assembly programs. It looks like nicer with a large bold heading, gray comments and red warning changes marked and reminders on to do in extra bubble fields. Some disadvantages here. You have to convert your text to a plain text at the end. You're using all your nice with design work, and your asserting text file should not have a single control byte left. Otherwise, this by a single byte will cause an error message when you assemble the text. And remember, line numbers here are only correct on the page on your source code. So whatever text programming tool is up to you. The following examples are written in Wave RAM, an editor provided by ATMEL in the early days. The plain editor field we type in our directives and assembly instructions. It is highly recommended that lines come together with some comments starting with semicolon. Later understanding of that, what we have planned here will be helpful in later debugging. Now store the program text name to something .asm into a dedicated directory. Use a file menu. The assembly program is complete now. If you did like to see what syntax highlighting means, I have a snapshot of such an AVR editor here. The editor recognizes automatically and uses different colors. Syntax highlighting to signal user constants and typing errors in those instructions in black. Storing the code in an .asm file provides nearly the same text file. Colors are not stored in the file. The editor is simple typewriter. Wave RAM is shown in figure. Don't try to find this editor or its other. The editor is a history and no longer maintained. Structuring assembler code. This shows the basic structure of an assembler program. The structures are typical for AVR assembler. This text discusses commands, header information, code at program start, and the general structure of the program. Command. The most helpful thing in assembler programs are commands. You will need to understand older code that you wrote sometimes years after. You'll be happy about having some or more hints what is going on in that line. If you like to keep your ideas secret and write them against yourself and others, don't use comments. A comment starts with a semicolon. All that follows begin on the same line will be included by the compiler. If you need to write comment or multiple lines, start each line with semicolon. So each assembler program starts like that, semicolon, semicolon, click.asm program to switch a release on and off each 2 seconds written by this commit last string 7.10.2 semicolon. Structuring assembler code, put comments around all parts of the program, be a complete subroutine or a table. Within the comments, mention the special nature of the routine, preconditions necessary to call or run the routine. Also mention the results of the subroutine in case you later will have to find errors or to extend routines later. Single line comments are defined by adding a semicolon behind the command line like this, LDI or section 0x0a, semicolon, here something is loaded, move or 17 or 16, semicolon, and copy somewhere else. Things to be written on top. Purpose and function of program, the other version information in other comments on the top of the program should be followed by the processor type that the program is written for, and by relevant constants by a list with the register name. The processor type is especially important. Programmers do not run on the other chip types without changes. The instructions are not completely understood by all types. Each type has to EEPROM and internal SRAM. All these special features are included in the header file that is named xxxx def.inc, where xxx being the chip type, SM2313, DN2313, RM8515. These files are available by ATMEL. It is good straight to include this file at the beginning of each program. This is done like that. No list, no list, don't list following into the script dot include M8515 def.in import of the file dot list, switch list on again. The path where this file can be found is only necessary if you don't work that much studio. Of course, you have to include the correct part to fit your place where these files are located. During assembling the output of a list of files, listing the results is switched on by default. Having listing OP might result in very long list file star.list. If you include the header file, the directive .no list turns off this listing for a while. List turns it on again. Let us have a short look at the header file first. These files define the processor type .device at mega 8515, the target and semicolon target device type. The directive .device advises the assembler to check all instructions if there are available for that AVR type. It results in error message if you use code sequence that are not defined for this type of processor. You don't need to define this within the program, as this is already defined within the header file. The header file also defines the registers XH, XL, YH, YL, ZH, ZL. These are needed if you use the 16-bit pointer XY or Z to access the higher or lower byte of the pointer separately. All port locations are also defined in the header file. So port B translates to a X number where this port is located on the defined device. The ports name are defined with the same names that are used in the data sheets for the S15 processor type. This also applies to the single bit in the ports. Read access to the ports B. Bit 3 can be done using its bit name pin B3 as defined in the data sheet. In other words, if you forget to include the error file, you will run into a lot of error messages during assembly. The resulting error messages are in some cases not necessarily related to the missing error file. Other things that should be on top of your programs are register definitions you work with. Example, .def MPR is over 16 semicolon define a new name for the registers 16 or 16. Structuring some code. This has the advantage of having complete list of registers and to see which registers are still available and used. Renaming registers avoid conflicts in the use of these registers, and the names are easier to remember. Further on, we define the constants on the top of the source file, especially those that have a relevant role in the different parts of the program. Such a constant could, example, be the external frequency that the programmer is adjusted for. if you use the serial interface on board with .eq port 000000 crystal frequency definition at the beginning of the source code, you immediately see for which clock you wrote the program. Very much easier than searching for this information in 1482 lines of source code. Things that should be done at the program start. After you have done the header, the program code should start at the beginning of the code. The reset and interrupt vectors, their functions, see in the jump section or place. As these require related jump, we should place the respective interrupt service routines right begin. In case of ATMEL types with large flash memory, jump instruction can be used here, so be careful there. There is some space left then for other subroutines before we place the main program. The main program always starts with initialization of the stack pointer, setting registers to the hardware and the unit of the hardware components used. The following code is specific for the program. Tools for structuring the program code. They describe standard structures included in the program written with our Windows operating system, which can be downloaded from the following site. Unzip the executable file and simply run it. It shows this. Here you can choose ATMEL by clicking on it and then select ATMEL30 in the drop-down field AVR type. You are now asked to navigate to the respective input file tn13def.inc. Show the program where the header file is located. Here you can enter your designed multi-purpose register, the output configuration on the port A and B if available, and if you want to use interrupts, click update to fill the window with your code frame. Click copy to clipboard if you want to paste this code into your code editor, or write to file to write this in an assembler code instead. If you don't know what it is for and what to do, press the L button. This produces the code. Add project title here, add more info on software version here, copyright 20 HS by adding copyright here, include a header file or target AVR type, no list. Include tn13def.inc header at tn13.place. Hardware information as commands, add all hardware information here, port and pins comment, add names for order ports and pins here, format .eq, port input is port A, .eq, control pin, port in is PIN, pin A, dot equal LED output pin is port A2, constants to change, add all constants here that can be subject to change by the user, format .eq constant, $ABCD. Fixed plus derived constants, add all constants here that are not subject to change or calculated from the constant format, .eq constant, $ABCD. Register definitions, add all register names here, include info on all used registers with specific names. Format .def RMP is over R16, def RMP is for 16 multiple register. SRAM definition D segment .org 0x0060 format label .byte n, that's n bytes for the label. Reset and int vectors .c segment .org $000 or jump main simple reset vector RTI RETI INT vector 1 or to INT vector 5 to INT vector 9. Interrupt services, add all interrupt service routines here. Main program init main colon semicolon init stack IDI RMP low RAM end semicolon init LSP stack out SPL comma RMP semicolon init port B IDI RMP 1 less than DDB2 1 less than DDB1 1 less than DDB0 or directions of port B out DDRB comma RMP, add all the other routines here. IDA RMP, one less than SC, enable sleep out, MCU CR RMP, SCI. Program loop, sleep, go to sleep, no up, dummy for wake up, or jump, loop, back to loop, end of source code. The assembler. Now we have a text file with blank ASCII characters. The next step is to translate this code to a machine-oriented form well understood by the AVR chip. Doing this is called assembling, which means put together the right instruction words. The program that reads the text file and produces some kind of file is called assembler. In the easiest form, this is an instruction line program that when called expects the addresses of the text file and some optional switches and then starts assembling the instructions found in the text file. If your editor allows calling external program, this is an easy task, if not another item on the wish list for the editor window to 2010. It is more convenient to write a short batch file again using an editor. This batch file should have the line like path to assembler, assembler.exe options, path to text file, text-file.asm. Clicking on the editor section of program caller or on the batch file starts the command line assembler. That piece of software reports a complete translation process in smaller window here with no errors. If errors occur, these are notified along with the type and line number. Assembling resulted in one word of code which resulted from the RJump instruction that we use. As a single ASM text file now has produced 4 other files not on up here. The first of these 4 new files is test.eep. All the contents that should be written to the prompt of the AVR. This is not very interesting in our case because we did not program any content for the prompt. Assemblers therefore deleted this file when we completed the assembly run because it is empty. The second file, test.hgx, is more relevant because this file holds the instructions later programmed into the AVR chip. This file looks like this as shown in figure. The X numbers are written in a special ASCII form together with the address information and the checksum for each line. This form is called Intel X format and is very old and stems from the early world of computing. The form is well understood by the programming software. Yes, the third file is test.obj, will be introduced later. This file is needed to simulate an AVR. Its format is hexadecimal and defined by ATMEL. Using a X editor, its content looks like this. Attention, and this file format is not compatible with the programmer software. Don't use this file to program the AVR. A very common error when sorting. .obj files are only produced certain ATMEL assemblers. Don't expect these files with other assemblers. The fourth file, test.lst, is a text file display its content with a simple enter the following results. The program with all its addresses, instructions, and error messages are displayed in a readable form. You will need that file in some cases to debug error. These files are generated only if the appropriate options is selected on the command line options, and if no list directory does not suppress listing. Programming the chips to program our Xcode as coded in the text form in the .x file to the AVR programmer software is necessary. This software reads the .x file and transfers its content either by bit or serial programming or byte by byte by parallel programming to the AVR's flash memory. We start the programmer software and load the X file that we just generated in an example that looked like this. Please note the displayed window stem from the isp.exe, a historic program no longer distributed by ATMEL. Other programmer software looks similar. The software will burn our code into the chips program store. There are a number of preconditions necessary for this step and several reasons possible. If this step fails, insert your programmer software if problems occur. Programming hardware and appropriate software alternatives for different PC operating systems are available on the internet. As an example, our program over PC's parallel or serial communication port, Pony Pro 2 version should be mentioned here. Thank you.